Hello, good morning, ma'am. Your mic is. Yeah, yes, ma'am.
Yeah. Are you
Good
audible?
morning. Yes, ma'am. You're audible.
Yeah. Good morning. How are you?
I am fine, ma'am. How are you?
Yeah, I'm fine.
Okay,
Yes.
shall we start?
Yeah, sure. Sure.
Uh,
So,
okay, good morning to all of you, dear participants and respected Dr. Premlata Jena, ma'am. Today we have Dr. Premlata Jena, ma'am, as an expert. So, I would like to just read his brief biography first. Dr. Jena has completed his B.Tech in 2001 and M.Tech in Electrical Engineering from IIT Kharagpur in 2006. She has earned an PhD degree from IIT Kharagpur in 2011. Uh, she has been awarded various awards in 2017. Recently, in 2017, she has been awarded as the Women Excellence Award from DST. In 2016, she has been awarded as Early Career Research Award from SERB DST, SERB DST, New Delhi. In 2013, she has been awarded as INAE Young Engineer Award. In the same year, she has been awarded as POSCO Award also, and she is actively involved in various projects, research projects, and research related to the smart grid technology and protection. And there, her area of interest is basically microgrid protection, signal processing, application to power system, relaying, power system protection, and protection issues with FACT devices, and so on. So today I would like to welcome Dr. Premlata Jena. She is with us, and now I would like to request, ma'am, please start your presentation.
thank you so much, Abjal. So, Dr. Abjal, these are not required at all. Thank you for inviting me. So, this introduction is not at all required. So, only thing is I can say it's a very good gathering. And sorry, I became late for 4 minutes. So due to
It's okay.
inconvenience.
You're welcome, ma'am.
I'm really thankful to your institution for inviting me. I'll try my best to deliver at my capacity, and I'll try my best to. It's a kind of like discussion will be from my side. Okay, so let me share this presentation first, and then I'll talk and start my views. Is it my slides are clear to all of you? Visible to all of you? My PPTs are visible to all of you?
Yes, ma'am. Now it is visible.
Yeah, is it visible? So, okay, so once again, a very good morning to all the participants and organizers, and thank you again for inviting me to this particular event. And my topic of this presentation is innovation towards smart grid protection. So, first of all, I'll just tell you a few things about this smart grid area, because Dr. Afzal is a PhD. He was a candidate in our institution at Roorkee. He has also visualized some of our challenging parts. When I joined at Roorkee in 2012, so my research area was in conventional transmission line protection and conventional power system protection. And I was afraid to start anything about the smart grid. So, but slowly when I came to know that this area is so important for all of us. And again, the smart grid protection is a very vital field of it. So why not the research can be extended in this direction? And many students, they came forward and they helped. So therefore, we have a very good team in our IIT Roorkee electrical department. So in this front. So, so if you see this first slide, you could see it's very clumsy kind of thing. Like you have on the left side, you have solar, you have wind, and you have like coal-based, and then you have some kind of residential.
Excuse me, ma'am.
Yeah, yeah, please.
Yeah. If it would be good, then it is full screen.
Yes. Thank you. Is it okay now? Is it okay?
Yes, ma'am.
Sure. So, so this pictures are very buzzy in nature, very confusing, isn't it? But honestly speaking, these are not that much of clumsy. If our direction, our understanding, our passion will be clear. So then I think these pictures will be very eye smoothing to us. And so this, what I'll do in my presentation, first I'll start to explain to all of you what is this smart grid first. I mean, we should know what is smart grid, and then only we can go for the protection of the smart grid. Okay. So I think up to 11:30, I'll try to push some ideas, some discussion towards the smart grid, microgrid, and then the second part, I'll start the protection issues and how to solve it. So before that, let us quickly have some glance, have some ideas or discussions where we stand as far as the energy is concerned. So in India, if you see, our installed capacity is around 370.10 gigawatt. And out of it, our coal is 55.4% and renewable is almost 23.5%. So what we are trying to do, our government of India, we have many policies, and in fact we have one branch, that is MNRE, that is the Ministry of New Renewable Source. So there, what the government of India is trying to access more energy from the renewables rather from the fossil fuel based generation. And if we just talk about the renewable sources, then by 2020, our generation or installed capacity is around 87.02 gigawatt. And our target is by 2030, India government is targeting around 300 gigawatt of renewable energy, which are going to be installed. And in fact, our major leading renewable sources are wind and then solar. Okay. And from wind, we are getting around 45.2%, and from solar, we are getting 36.7%. So this figure is quite small. If you see our contribution, our demand. So what is the demand? I mean, the demand, if it is increasing exponentially, so obviously our generation should also follow the trend. Otherwise, there will be a gap between the generation and the demand. Okay. So therefore, this information is important because the worldwide the installed capacity is forecasted. Basically, it is projected by 2030. It is going to be 7,000 gigawatt. So this amount of energy, do you think is a small number? Not at all. So this is a very big, huge number. 7,000 gigawatt of energy is a requirement. And that's true. It is seen that the researchers, they have forecasted, they have undergone that mostly in the Asian continent, and that's in India, like countries, developing countries, the energy demand is quite, exponentially increasing in trend. And so to meet this energy trend, so it is very essential to have some energy exploitation from the renewable sources rather from the non-renewable sources, which are actually exhaustive in nature, and anytime it can be finished, it can be existed. And so therefore we have to go for alternative paths, alternative energy ways out. The point is why these are concerned in the smart grid, because the renewable sources are basically mostly very intermittent and very uncertain in nature, very versatile, you can say, like solar, wind. You have thermal, geothermal, you have tidal energy, you have biomass. Although this biomass and other things like fuel cells, so those are actually renewable, non-variable. See, there are two types of renewable energy sources. One is the renewable source with variable in nature, and renewable source with non-variable in nature. Now, what are those renewable sources which are non-variable? Basically fuel cell. So we know this is my hydrogen content in the in my cylinder, so I can just produce this amount of energy by this time. And similarly, if we have some like biogas and biofuel, so from this bio plants, these are my content and these are my input products. So from there I can get this amount of output energy. But at the same time, the solar and wind are very uncertain. So those are known as variable renewable sources. So whatever it may be, but finally our main aim, our main goal is to achieve maximum energy from the renewable sources, it may be a variable in nature or variable in nature, instead of accessing more power from the coal or maybe nuclear. Okay, so that is what is, we have to reduce the carbon dioxide emission or footprint, and we have to reduce the pollution rate, and we have to also reduce many poisonous gases which are coming from this diesel, petrol, or your carbon dioxide based, coal based plants. So, so now question comes, why many researchers, they are motivated towards the smart grid era, a smart grid technology. I'll just tell you one simple example before that. In many classes I discussed this. And so there are many blackout events, but I'll take the example of our country. So recently also in 2016 in Australia, there was also one blackout. And of course, many countries like US, like Afghanistan, Pakistan, so there are Canada, so and Australia, so many countries, they're facing this problem. But the point is, in India, in last 2012, July 31st, there was a line, 400 kV line, and that line was joining from Bina to Gwalior. Okay, so that line was basically connecting from the western grid to northern grid. Fine. So what happened? Due to the overdrawing of the power, okay, so there is a huge amount of power demand on the northern grid side. So as a result, that particular line was overloaded. And that line was overloaded. So as a result, what happened? And that line was basically misleaded. One of the distance relay, if somebody is working in the area of protection, they may get it quickly. That distance relay was maloperated due to the load encroachment problem. So what is this load encroachment problem? This distance relay has 3 zones of trip: zone 1, zone 2, zone 3. And this zone 3 basically maloperate during the loading, heavily loading of the line. That is known as load encroachment problem. So when this line was overloaded and the zone 3 unit of the distance relay came to know that yes, it is something else, maybe a fault, maybe load encroachment problem, but whatever it may be, if it will enter the region, the trip region, that means the relay will trip. That's all. When the relay will trip, the line will be tripped. It will be open. So what happened? When the line tripped, suddenly the power from the western side and through other lines also tried to flow through the northern side. And slowly the lines which are actually should have carried some less amount of power, they carried large amount of power. So as a result, there was a cascading failure of lines, and total northern grid was disconnected from the western grid. And there is a mismatch between electrical demand and the prime mover input in the northern side of the generators, and then the generator is bound to sit down. So what happened? Totally the northern grid and northeast grid together are under blackout condition. So this kind of situation, it may be very astonishing. Yeah, it had happened before 8 years, but honestly speaking, it takes all the money or the cost invested for the last 20 years, 10 years. So though this kind of disturbances are very rare, but once it will happen, so obviously it will take all the cost. So which is very expensive for the government as well as for the customers. So therefore, to just overcome this kind of disturbances, the government of India has laid a task force to investigate how this basically the blackout had happened, what are the reasons behind it. Okay, so they got it. So finally they got, due to small distance relay protection failure, it had happened. So we have to very just construct or design or some laid some very strong, reliable protection technology for this kind of, to overcome this kind of disturbances, right? So this is how during that time some of the areas in the NCR like Delhi and Delhi Metro and the airport, so those are the critical loads which are actually disconnected from the main grid knowingly. Intentionally islanded areas are created to save those. It help us to overcome such kind of major disturbances, and also to reduce the carbon dioxide emission or carbon dioxide footprint and to some extent the pollutions in the environment, because the ecological balance should be maintained. So many things are there. So, but this is somehow some introduction to the motivation. And most importantly, why this smart grid is required? Because this right figure you can see, this right one. In the x-axis we have taken this size of interconnected grid, and y-axis I have taken this benefits and efforts. So now you may question that you don't think that the present grid, which is in operation, it's not that smart. It is not that much smart. So you can see from this picture itself, there is some pressure on the present grid. So therefore we are going to remove that pressure and we have to make it smart. But honestly speaking, the present grid, earlier it was smart, but due to the demand growth, as I said in one of my PPT, the demand growth is exponentially increasing. So you have to supply those demand. You cannot stop it. Suppose before one day, I mean, maybe before 1 month or 2 months or 6 months at our home, we have connected one AC. But again, due to some problem, again we have connected 2 ACs. So then one more AC demand has increased. Just very simple example I'm telling you. You can think of other customers, like you have industrial build. Every day we are increasing our industry requirement. Our commercial sites are increasing. And most importantly, we are increasing our transportation part. Sorry.
Adi.
Okay, so sorry for the interruption. So now if you see that this present grid is basically AC grid, and we don't have any DC grid. So in this case, I just want to say one very important point to all of you, that why this existing grid is not that much of efficient to meet our demand. So from this picture, you can always understand this point. So here you can see that in your x-axis, we have size of interconnected grid, and along y-axis, we have benefits and efforts. So if your size, what do you mean by size of the interconnected grid? Maybe voltage-wise, maybe power-wise, it will increase slowly, okay? So or your size means maybe number of buses-wise, transmission line length-wise. So if you further increase the size of the grid, initial stage it is fine. See this line, this red one is the efforts curve and the blue one is the benefit curve. So this is my effort. So I'm getting good benefit, isn't it? And in between it is optimum. This is also fine with increase size of increase in the interconnected grid size. So but at the end, further if you increase the size of the grid, what will happen? The advantage basically to decrease. I mean, your effort is this much, the red one, but however your blue part is very close to it, and this gap, effort benefits, I mean the benefits are very less. So that means I'm putting more effort, but I'm not getting the proportionate benefit out of it. So therefore, this is only one in pictorial understanding. But apart from that, we have many other issues for which the present grid is under pressure, and definitely we need some flexibility in the existing grid. The first one is we have a very increasing grid size and complexity. And we have very demand growth, as I said, it is increasing exponentially, and increasing energy trend, changing load flows, bulk power transmission, bottlenecks and overloads. It is obvious because in India you cannot stop it. So you have suppose one corridor, we'll try to push as much as possible power from one area to other area. So as a result, the lines are actually heavily loaded. It is going to be heavily loaded in recent times, because what happens when some industrial belt you are going to make, you are going to just stand, or some commercial sites you are going to stand. So what will happen? You have to access the power from the nearby cities or nearby your substations. So in that case, what will happen? So obviously the existing infrastructure will be overloaded, and that is not desired. That is not a good sign. As I said to you, all of you from the beginning, this blackout, this kind of disturbances are going to happen every time. Even I could remember a very simple example I always give to everyone, that in our village areas, so due to the theft and some kind of other activities, the transformers which are installed, they are actually overloaded, and the transformer actually burnt sometimes. So then the supply to those areas, remote areas, actually stopped for month to month, isn't it? So this kind of things we should avoid as much as possible to make the present grid smarter. So definitely some flexibility is required, and without that, this without the smart grid technology or microgrid technology, this is not possible. Okay, so therefore, finally, I'll just give you some definition of smart grid, and then we'll come to the microgrid. What is the definition of microgrid and the protection issues? Now, in US also in 2003 there was a huge blackout, and then they laid some policies for that, and from that policy they have decided that we have to keep some kind of some logistic approach, some technical approach, some smart approach, so that we can avoid such kind of major disturbances in our network, and we can make our lifestyle more reliable, supply system more accurate, more sustainable. So these are some of the summaries I have collected from there, like increased use of digital controls, avoid the analog controls, because analog controls are basically sluggish in nature, and their communication from one domain to other domain is also difficult. Okay, but in digital controls, it is faster, it is dynamic, and it can also communicate from one station to other station. Digital, because of course, the digital data, now the digitalized world, so the platform, the medium, the equipment should be also digital in nature. So they thought of in that way, so why not make the equipment and controller, everything in the digital platform. And very dynamic optimization process would be no static operation or static approach. And we should integrate more distributed resources. These distributed resources means like you have the renewable sources and battery storage. Demand response, then smart metering. So now the government of India is trying to have this smart metering facility, you have kind of smart appliances, storage and peak saving, customer control, communication standards, reduce mark barriers. Okay, so these are some of some of the very important topics what I shared with all of you. So you have to also read more on about. So this kind of responses basically like customer control, communication standards, reduce market barriers, and so many things are there. So many things are there. Just I'll discuss a very important point here, which one I have decided. What is this customer control and storage peak savings? See, actually what happens during our peak hours, generally the generators, fossil fuel waste generators actually stressed. So we have to there's a dog curve, we call it a dog curve. Dog means if our demand is very high at a certain point and we have to supply that particular demand. So why not we will exploit that demand from the renewables or maybe from the storage devices. So what will happen? As a result, our customer, I mean, that time what happens, I'm telling you another point also from the research, that during that time, the agencies, the utilities will demand more money. Per unit cost will increase. So why not I'll just extract those energy from storage devices or some kind of renewable sources. So, so this is, am I audible to all of you? Is it okay? Abras, is it okay? Hello?
Yes, ma'am, it's audible.
Yeah.
Yes, ma'am.
Yeah. So, thank you. So now they also went another customer control. See, actually, earlier what happened, let me tell you one more point regarding the conventional grid, that in the conventional grid, what happened, the power flow was unidirectional. Centrally, there will be a generating station, and let us say after 2,000 kilometers away, the customers are located, so there the power will be delivered. Right. So in that case, what happens? The power is flowing from 2,000 kilometers away from the load centers. If anything will happen to the loads, the disconnection of the power, something, the customers are not able to inform to the utilities also, isn't it? So to avoid such kind of issues, right? So very easy operation of the customers and the utilities. So this microgrid concept comes to the picture, and I'll tell you what is the relationship between this smart grid and microgrid. Microgrid is nothing; it's a pocket. The smaller part of bricks, building bricks of your smart grid. So when many microgrids are interconnected together smartly, then the smart grid stands. So and they decided this. Why not the customers would have also the same rights, same flexibility, and same kind of enjoyment they should do, and they should also control to the utilities. Not only the utilities will control to the customers should also control the utilities. In US, there is a scheme like we are taking this Geo SIM or some Airtel something. The US, they can also punch their card and they can just energy card. So I'm earning 6 to 8 some kind of utilities. They have per unit cost is very less, and they will just access the power from that agency. And again, 6 to 10, 8 to 10 some other agency where the cost is less. Now that kind of flexibility is there with customer. So this is only possible using this smart grid technology. And some kind of communication standards also they have maintained. And of course, in the conventional grid, there is no communication flow from the customer to the utilities or utilities to the customer. And there is no storage also. Sorry, the storage is very important now. So without any fail, there are so many pilot projects are running in the country how to have a very good advanced technology for the storage system. Lithium ion or supercapacitors or some other flywheel based storage or some air compressed, water compressed, whatever. The storage, pump storage power plants. So we are trying to have a new technology so that we can store the energy for our requirement, just like we store our water. With a requirement, we utilize it. So of course, these are very challenging tasks. We are not saying it is very easy. Just like speaking, it is not that much of easy. Okay. So and reduce the market barriers. Like now, nobody can stop me. Okay, so Geo cannot say no. I am the whole sole authority of this SIM market. He cannot say, because I have all the possible freedom. I can either enjoy the Airtel facility, I can enjoy the Geo facility, or I can enjoy the BSNL facility, whatever. So that the market scenario is going to be like that. Market will be full flexible, and customers can participate in a full flexible mode, and utilities will also participate in a full-faced manner. So those things, you don't think that it is very cumbersome and very challenging? Yes, that is challenging. Therefore, we have to develop such models So where this kind of free environment, free market system can be developed. And that is only possible through the development of this vision of smart grid technology. Okay, so this is the very well-trained definition of the smart grid. So when you combine this information technology, we call it as ICT, information technology, communication technology, and along with the advanced dynamic controllers, intelligent controllers. I said 2-3 words to all of you. First, it should be dynamic, it should be adaptive, it should be intelligent, and it should be automatic. So there are 4-5 features or characteristics, you can say, of the controller. The controller is not static. It is not kind of sluggish in nature. It should be very, very fast. It should be automatic. It should not be manual. Somebody will the controller will wait. Some operator is going to switch on the button, then it will operate. It is not like that. So when those concepts like information technology, high-end information technology, it's not low-end, very high-grade processors are involved. And you have very dedicated communication layers and sensors, intelligent controllers. Those stuffs we are just marrying to the existing network. We are just combining with the existing network. Then what will happen? And there will be the generation of there will be the birth of smart grid era or smart grid technology. That is what is our aim. And this is not a bookish knowledge or paper writing or something. It is happening. And from this, we are trying to efficiently deliver a sustainable, economic, and secure electricity supply to the customers. So what do you think? What do you mean by this? So this sustainable word is coming to picture due to the presence of variable or non-variable renewable sources or storage devices. So if it is not there, then it is not sustainable. It is not sustainable. And at the same time, the supply system to the customer should be economic and secure in nature, and also should be efficient and reliable. So we have a global smart grid federation. You can search, you can go through the website. There are many countries like Europe, America, Canada, India, so many countries actually participating to charm what is the status of this network, the smart grid network. How much technology, how much we have progressed in this direction as far as the smart grid technology is concerned. So they are just time to time, they are meeting and they are discussing and updating to all of us. So this is how the definition, another definitions of Department of Energy, US and Wikipedia. So the definitions, what? Definitions are coming only from our realization. Definitions are not just like, as I said, bookish knowledge. Somebody has just written like this. These are coming from our own realization. Okay. So therefore, this smart grid is basically a vision, and it is not a product. As I said, many forums like this smart grid is not a product. Somebody will make for you, and you have to enjoy it. It is not a service. I'll just put in to your door, and you will enjoy it, or I will enjoy it. But it is not like that. We have to be very proactive, and we have to be ready to accept all challenging issues, and researchers, should be ready, industry personnel should be ready to take over all the challenging projects to bring to the field implementation level. So that should be our vision in this regard. Okay, so next my point will be, from the first part, I decided wherever I just try to convince, discuss in the smart grid forum, I try to place some initial ideas. So straightforward, we cannot start the microgrid protection, smart grid protection. I hope many of you know it, but still it is my understanding that we should discuss little bit initial portion. So which is actually our, before starting our exercise like running, so we do some jogging, warm up exercise. So now our mind is ready that why this smart grid is necessary, and why this microgrid is coming to us, what is the necessity of it. Okay. So what I'm trying to say, while we are formulating some problem for research, we should understand A to Z of the problem. We should recognize the problem properly. Then only we can give some good solution to that. And if we do not understand the problem, so how can you give some good remedies? Like the doctor, he understands, what is the problem with the patient, and then he diagnoses properly and he gives some medicines. And accordingly, it will be cured and the patient will be cured. So similarly, we should understand where is our problem, what are the problems, issues. Then we can diagnose. We could diagnose properly, and then we can give some right direction. So this microgrid, as I said, in between of my discussion, I said that earlier our conventional grid was a centrally located grid, right? And we used to push power from the very high end, for like 2,000 kilometers away. Like here, I'm sitting here in Roorkee. We have nearby TSDC, the Tehri hydropower plants. And this Tehri is pushing power to Delhi, and so maybe more than that, some distance. So around 500, 600, 700 kilometers. So the concept is during this transmission process, we have huge amount of losses. Around 10 to 15, 20% losses we are getting. So what the researchers or the industry people, they are thinking together, why not the supply system should be close to our customers? What's the problem with that? If you keep our like a solar park near to Roorkee town, so this Roorkee town, the city, will get the supply from a small solar park nearby. So maybe around of 10 megawatts, 20 megawatts, 30 megawatts, 50 megawatt. Okay. So this small chunks of power pockets, basically inside this power network or pockets, you can say those are called as microgrid. So this micro means 10 to the power minus 6 millimicro. So if I ask to one of you, what is the capacity of the existing grid? Kindly excuse, maybe some of you maybe not necessarily from power system background, and therefore I always try to make my presentation little bit generalized, so that other people from other background, they can understand it little bit. And so this, when I ask to one of you that what is the rating of a existing grid, and of course the answer will be in the range of gigawatt, isn't it? Now, so this gigawatt, as I said from the first of my slide, our installed capacity was 370 gigawatt. So micro means if you multiply this gigawatt by 10 to minus 6, so the power level will be reduced to megawatt or kilowatt. So this smaller version of the grid, which handles the power range up to, according to IEEE standard, this microgrid, around 50 megawatt. IEEE standard series you can follow, all of you can write also. IEEE standard 1547.1.2.3. So all the rules and regulations, standards, lines are provided over there. What is smart grid? What is microgrid? What is its rating? Voltages, powers, converter-based renewable sources like solar, wind. What should be the size? What should be the? All the regulations are mentioned over there. So this microgrid, one understanding, layman understanding, as this micro, if you multiply with the gigawatt range, so the power level will be reduced. So the grid which handles the power in the lower range, like in the up to 50 megawatt, so those grids we called as microgrid. That is one definition. And of course, the voltage level is up to maybe 11 kV or maybe some low voltage microgrid, high voltage microgrid we have. So this low voltage, maybe in the 400 volt also level we have microgrid. Maybe in the 11 kV level, 33 kV level we have microgrids, AC microgrids I'm talking. Because our Indian power structure is mostly laid on AC grids, in AC infrastructure. And one more definition of this microgrid is It is an interconnected system consisting of interconnected loads and distributed energy resources. So what is this? So and which as an integrated system can operate in parallel with the grid, or it can operate intentional islanded mode. What is the meaning of this? When you have a chunk of renewable sources, batteries, loads, so those interconnected network is known as microgrid. And those interconnected network, microgrid can either operate in connection with the grid, that is known as grid connected mode of operation, or it can be disconnected from the main grid and can also operate in islanded mode. Okay, that capability should have. So this environment is also known as microgrid. But in microgrid, we should have the battery storage system. Then only it can be called as microgrid. So this is next comes the mini grid. Many times I just want to share this type of information. When I was studying this smart grid, I was just scratching from the, even now also we are scratching from the level, basic level. So it helps in some extent in our research and also in industry belt if you understand from the basic level. So instead of going to a very high class theory without knowing the basic level theory, so it creates problem. So so our procedure of movement should be like this. So therefore one more term also comes to picture along with the microgrid, that also we should know. If you are doing some research in the microgrid or smart grid controller, topology design, or some protection, stability. So I'm just talking for the electrical point of view. But a smart grid is not a one-man show. There's many electronics engineers, many other chemical engineers. They are for battery, for physics people. So many, honestly speaking, many people are now dedicated for this components of the smart grid. Okay, so this mini grid is what? You can see this picture. Is it visible to all of you? Is it visible, my PPT?
Yes, ma'am.
Yes.
Yeah. Yeah. So this mini grid means, I said microgrid, so mini is further reduction. Okay. In mini grid, you have the solar photovoltaic. And the main speciality of this mini grid is what? It can pump the power without the presence of the main grid. You have a solar photovoltaic here, and you have multifunctional inverter devices, and then you have the storage, of course. As I said, whether it is a mini grid or microgrid, the storage should be there. And from there, because the solar output is DC, so it converts DC to AC through this inverter device. And a transformer is there, let us say 400 volt is the output of my inverter, so it will convert to 4.1 kV also. Now, so this transformer, it goes to agricultural processing facility and some residences. So what is it? Like I have seen in many other remote areas like South Africa and some other US and New Mexico. So in the remote downtown cities or villages, so they have this kind of facilities. Even Switzerland also, they have some sort of, the substations are very well distributed. It is not centralized substation. They have distributed substation. Here one, here one, here one. They have different grids. We have 5 national grids, but their grids are distributed here and there in Switzerland also. So there's some villages, some grid will supply power. Some other towns, some other grid will supply power, like this. So similarly, when some sort of residences, few residences, residential areas, and some agricultural facilities, mostly this is dedicated for remote end grids. Remote end areas means where the main grid has no accessibility, it is far away from that region, then this kind of mini grid helps supplying the power. But here you could not see very mega scale industries or mega scale cities or mega scale commercial sites. And this kind of energy supply is maybe for 8 hours per day is sufficient for all of them. And cost will be also cheap. And of course, there is a battery. During night time, they can also utilize it. And now the concept is coming hybrid renewable energy supply based mini grid. What is that? along with the solar, so they will connect a wind system. Okay, that is known as hybrid solar wind renewable source. Okay, what will happen during night time? During night time, if you have suppose your solar energy is absent, then the wind energy will come. So what will happen? So through day and night, this mini grid will get supply. But the disadvantage, this kind of operation is known as standalone mode of operation of the grid. But we don't have any access to the main grid. This is the major disadvantage. So this can go up to 10 kilowatt to 10 megawatt, and the voltage level is up to 11 kV. So now what is nano grid? So this nano words means 10, again further reduction, it is not macro, further 10 to minus 9 if I'm not wrong. So nano is further reducing the power, and from gigawatt level, just think about it. So it is quite, very interesting that how we are scaling down the power and the network to a very low level, and even it is to near to our home itself. It is quite interesting. And earlier, as I said, the many times also I used to say the utilities, they think that we are the king and the customers are the servant. So now the scenario has been changed. The customers can play any game, any role, and they can also play with utilities. So this kind of scenario is coming very soon. This nano grid is nothing, smaller version of the mini grid. A single building, just like we are sitting in this tower, this building itself will act as a nano grid. And their consumption of power rate is up to maybe less than 50 kilowatt, in the range of kilowatt. Hardly our home, inside our home, like Roorkee is just like a microgrid or mini grid, you can say. Its consumption is up to 8 megawatt. So inside a single buildings in our institution, it consumes maybe 100 kilowatt, some 200 kilowatt. Together, if you combine 3-4 buildings, 5 buildings, it may go up to like 100 or 200 kilowatt, like 1 megawatt maximum, half of the buildings, or less than that. So total consumption in our IIT Roorkee campus is around 8 megawatt. So out of it, we are getting 1.8 megawatt from the solar rooftop installed energy system. So this kind of system is slowly building up. So a single building can also get some power from its own utilization, and also rest of the power it can also sell to the nearest buildings also. So this concept is coming very soon. So let us see how much we will be successful, that we don't know, but we should be always aspirant. We should always forecast the best and positive things, right? So now you can understand, I started with smart grid concept. So here it is, your nano grid is a small blue person, the sky one. And many nanogrids, when combined together, they constitute one microgrid. And this total, many microgrids are connected. We call this a network microgrid. They just made it the main grid. Okay, so this is how this nanogrid structure. You have renewable sources, non-renewable sources, energy storage. And of course, in nanogrid, you have the availability of the main grid also. Many loads, gateway, and you can from there. So the gateway, there's a communication, and you can supply to the power utility entity or external agency. So this is how this nanogrid concept is built, and it is IEEE standardized, and you can also test in your laboratory also. We can also have some, we in our laboratory, we have developed to some extent, but it requires more dedication beyond that. So this is actually a smart meter which connects the grid, and we have also, along with this grid, we have also 2 more parallel generators like solar PV panels and energy storage. So these 3 are basically the energy sources. And from the solar, this PV inverter, through the PV inverter, it will go to your AC bus. This one is the AC bus. And bidirectional converter is connected with the storage, because this bidirectional converter helps in just basically when the battery is charging, so charging, it will just take the power from the AC grid, and with discharging, so it will just supply the power to the AC grid. Therefore, this is bidirectional converter. And then you have, of course, why this converter I have written. So this is AC bus. Either you can supply some DC loads or you can supply some AC loads. So if it is an AC load, what will happen? This will be again this conversion is some simply AC to AC. But if it is a DC loads, so then this AC to DC conversion will be there. This is inverter. Okay. So this is how these things goes, and now I'll come to this thing. As I said, that microgrid made up of multiple nanogrids, many buildings together in particular residential area. They just make some microgrid, and many microgrids together inside a district. They make a smart grid. So this concept are coming very soon. But let us say we have to build a very good policy. The government should make very good policy for this. That is important. Okay. So now these are some of the microgrids in India we have in operation. We have campus and institutional microgrid, just I said. In Roorkee, we have campus institutional microgrid, but honestly speaking, this is not to be called as microgrid in Roorkee campus because we don't have that storage facility till date. And we got some project from Mission Innovation and the Mission Innovation from DST. We are just looking the weak points in this microgrid where we can keep our storage devices so that then, and it should be fully automated, then only we can call it as a smart grid or microgrid. And again, the solar panels which are mounted on the rooftop, they are also not optimized. Why? Because optimum power we are not extracting from these panels, right? So only the panel and the inverter. There is no DC converter. There is no MPPT. So therefore, we're trying to optimize to make this full-phase smart grid structure. Okay. Similarly, the military base also, they are very believing this concept, and military base, they are also investing more money on this renewables. Honestly speaking, there is a cyber attack concept is coming now. What is cyber attack? Because this is not my talk, today's talk, but the cyber attack, basically what happens, it will just, it will puncture or it will just make such things, some mistakes or some disturbance in the main grid supply. So the military base is a very important load which should not be stopped at any point of time. So what will happen? You need some backup supply. And that backup supply should be your captive power plant, like solar or some kind of wind or some kind of storage facility or some kind of fuel cell, geothermal, or if it is not geothermal, then you can go for biomass based. So those renewable sources are going to be, see, actually I didn't take the name of diesel generator, but diesel generators are very common backup supplies. But how we can remove those diesel petrol concept, fossil based information, okay, energy belt. So how I can extract more energy, maybe in the main supply or backup supply from the renewables, that should be our target. So we have also remote off-grid communication, community utility, commercial, industrial. So our major target is goal is whatever the sector it may. But major concern is how to utilize the renewables optimally, efficiently for the smart operation. So I'll come to this protection part. Afzal, if you'll allow, then I can take for maybe 5 to 7 minutes break, and then can I start? Afzal, Dr. Afzal. Hello? Am I audible, Afzal?
Yes, ma'am, you are audible.
Yeah, shall I go for a break or I'll continue?
Yes, ma'am, you are audible. Sometimes some network issue may be there. Yes.
Yeah, so shall I move again or
Yes,
we
ma'am.
go for a break for 5 minutes?
Yeah, sure. It depends upon you and participants also. If someone is interested, we can have some query. Otherwise, we can have one break of 5 minutes.
And then for 1 hour we'll continue this
Yeah,
protection.
sure, ma'am. Sure.
So maybe 5 minutes we should take some break. Then I'll again go. Okay?
Yeah, definitely, ma'am. Okay.
Yeah. Thank you. Okay, Abdul, am I audible?
Yes, ma'am, you are audible.
Okay.
Yes, ma'am.
So my PPT is visible to all of you. Yes.
Yes, ma'am.
Yeah. So let us start this second part of this conversation or discussion, that how to protect this converter-based smart grid. Now, let me tell you that there are many issues. Like when we talk about the smart grid from the first part, we enjoy the concept. So everything was in very high-end concept. But when we go for real application, real field application, maybe in simulation, maybe in industry based, so we faced many problems, many issues are coming up. So there are many other issues. Because as my research presently, I'm just focusing towards monitoring, protection, control of the smart grid, DC microgrid, AC microgrid, smart grid. So I'm just trying to give some ideas, indication to in this direction, because it is very vast. Like somebody is working also stability of the smart grid, converter topology design for the solar system of the smart grid, controller design for the converter inverter of the smart grid or microgrid. Or somebody is working also in the power quality issues which are associated in the microgrid or smart grid. And many people, they're also working towards designing the solar cell, specifically wind system, okay, wind energy conversion system, WECS, fuel cell based operation. Then battery storage is very important, how the people are also being motivated now. The electric vehicle is an important aspect now. We have like 5 load centers, like 5 load segments. The first one is the residential customers, and we have then next agricultural customers, we have commercial belt, we have industrial belt. In industry we have low industry and high industry, high level industries where the power consumption is quite large. And again we have transportation belt, because it is seen that from the transportation around 20-30% losses are coming up. And so to overcome these losses, so we are basically, the government of India has planned or launched many schemes, and basically encouraging many researchers, institutions, industries to have quick research technology, and which will be cheap for the the market price of the electric vehicle should be less in comparison to your petrol diesel based engines. Okay, so that the losses can be removed, and so therefore, depending on many other aspects, seeing the, as I said, the smart grid is very vast area, ocean type thing, and you cannot say this is a very small thing what I'm talking to you. So this protection is one of it. Many issues are there. So we have to handle those. Somebody is working the charging station design of the electric vehicle, controller for that. So battery storage system and its battery management system design. So many operations, so many things are going on. Okay. Now the protection is one of it, because I heard this protection architecture, protection mechanism, or protection ideas actually are very vital. As we are playing, suppose cricket, if you're not wearing this helmet or some pads, or so then you cannot protect yourself. Similarly, when you're constructing or designing some network, power, electronic, or maybe power grid or smart grid, so definitely we should have at least a very good dedicated protection layer for that. And I heard that from the industry personnel that around 5% cost of the total infrastructure goes for the protection infrastructure. So this is not a very small amount. If it is a crores of range money we are investigating for the smart grid layer, so out of it 5% should be invested for dedicated protection infrastructure for that. Okay, so this protection is one of the important organ of the smart grid layer or system. So out of it, many protection issues are there. So first I'll just introduce you islanding detection concept, and then I'll talk to you the some which are actually happens like in a false tripping, blinding. Okay. Now, very simply,
Excuse me, ma'am.
Yeah.
Ma'am, please maximize your presentation.
Yeah, sorry. Is it okay now? this is one of the protection issue. What is this islanding? First, I'll tell you. It is one of the major research area now, and maybe it was a concept as before 10 years, 20 years, but now still it is very, need, and it is very essential field also. So what is this islanding detection? First, I'll tell you. Let us say this is your microgrid. As I said, definition of microgrid, we should have the renewable sources like solar, you should have some wind, you would have some batteries and some critical loads, linear, non-linear loads, unbalanced loads, many sort of loads are available here. And this microgrid, which is connected to the main grid through a PCC, and what is PCC? PCC is the point of common coupling. It is a very first point where the microgrid connects the main grid. Just it touches the electrical connection point of the main grid, the microgrid connection point. You cannot say this point, see my cursor, this is not PCC. PCC is the point where the microgrid touches the main grid. Fine. So, if suppose there is some fault or some disturbance in the main grid side, fine. So, what will happen? As these renewable sources, batteries are also sources of energy. So, they will try to push, they will also try to contribute some fault current to the main grid side if this switch is closed even then. So, what will happen if these devices are going to transmit? I mean, they'll try to contribute some power to the main grid, because where is the fault? The fault point is basically having the lowest voltage point. The voltage at that terminal is less. So, the power flows from the higher voltage terminal to potential to lower potential. So, now what will happen? What will happen? This renewable sources and storage together, they will try to push more current to this main grid side disturbance. Now, what will happen? The equipments which are associated with this renewable sources will be damaged. So, therefore, once there is a fault in the main grid side, the switch should be opened, because the switch belongs to the substation of the main grid. Okay, and so this main grid should be responsible to open the switch as quick as possible. Neither the renewable sources will contribute any power, or not the main grid will contribute any disturbance, or nothing, no interaction should be there. So what will happen as a result? If you are opening this species, this circuit breaker, so this microgrid is going to be disconnected from the main grid, and this disconnected operation is known as islanded operation of the microgrid. Now, if it is islanded, so islanded means it is not connected now with the main grid. This condition is known as islanded mode of operation of the microgrid. But now, you can write it also, the islanded mode of operations are of two types. Whether you are doing unintentional islanding or you are doing intentional islanding. That also matters. So, now, the unintentional islanding means what? The unintentional islanding, what I discussed with you, this one. The unintentional means, suppose your main grid is having disturbance. So, I am just opening this circuit breaker. So, my microgrid is disconnected. Okay. Unintentional, why? Because my main grid is having some disturbance, automatically this breaker will be open. I didn't do it intentionally. Okay. This is known as unintentional islanding. But when there is some main grid disturbance, but see, this is only one microgrid I have shown. Let us say you have bunch of many other microgrids. So, I'll just try to open my breaker at certain point where some areas will be disconnected from the main grid, but those areas which are disconnected from the main grid will operate smoothly without violating the voltage and frequency disturbance. And some areas where I'll just disconnect from the main grid because there is a disturbance in the main grid, so those areas will operate nicely without violating the power quality issues. So those intentionally making small islands is known as intentional islanding process. Just I was giving one example during this, a very simple example during the last blackout in Delhi, Delhi Metro and the airport and many other critical loads. So they are basically disconnected from the main grid and they operate in an islanded mode, and they get a supply from the backups. So this kind of system is possible. But those are not, the islanded areas are made basically intentionally. Okay, sorry. So this intentional islanded areas, unintentional islanded areas, what is the difference? The question comes. If it is unintentional islanded mode of operation microgrid, my voltage power mismatch between the generators, renewable sources, and the loads may be different. There is no balance in unintentional islanding. But intentional islanding, I did some sort of pre or offline study that if any disturbance comes, so from here my circuit breakers will open so that the rest of my network will be balanced when supply and the load demand will be equal, and there will be no voltage and frequency violation. That is my intentional islanded mode. And this intentional islanded mode of microgrid is also two types, scheduled and unscheduled. Okay, so now I'll talk to you on intentional islanded mode. Just now you take example. This is actually microgrid where let us say you have 100% load and 30% supply is supplied by these renewables, and rest of the 70% you are getting from the main grid. So when this main grid is off, so 70% load is you're not getting, your supply is 70% supply is off. So only you are getting 30% from the renewables, isn't it? So what will happen? The rest of the 70% is missing, so that means there is a mismatch between the active and reactive power, the generation and the load. PL, that is known as delta P, delta Q. This delta P, delta Q is nothing, change in active power and change in reactive power. Delta P is nothing, P generation minus P load, and delta Q means Q generation minus Q load. We call it as mismatch in power. Now, if your generation is low, low demand is high, so this delta P will be negative, isn't it? Because delta P is P generation minus P load. And similarly, if your generation is large and load is less, demand is less, so your delta P will be positive. So this concept, from there, we develop one concept known as NDZ, non-detection zone. Okay, so what is that? I'll just tell you quickly in the rest next of my slide. So this due to this mismatch in the reactive active power, remember in microgrid at the low voltage level microgrid, your due to the reactive power active power mismatch, the voltage varies. Why? Because it is highly resistive in nature, and for reactive power mismatch, the frequency varies. This decoupling factor comes to picture. So we have actually developed one centralized microgrid controller which takes care of many adaptive islanding schemes we have developed in our research group. So I'll discuss one, two of it. So now here you may ask me, what is the reason why this mode of operation, this either the microgrid is operating grid connected mode or it is in islanded mode. Again, you are talking on intentional islanding mode or intentional islanding. Why these are required for us? What a necessity that these are required. Because if it is a non-intentional islanding, if you do not know that operation, so your voltage and frequency will be affected due to the mismatch in active and reactive power. And those will create the problem for what? For your power quality issues. The first problem I'll tell you, here I have written some of the problems. Here you see. First of all, due to this unintentional islanding, out of phase reclosing will be there. Out of phase reclosing means suppose you have one when the grid is off. So this side frequency will be something different. The grid side frequency will be something different. When you are going to close it, then it will create a problem. Out of phase. Degradation power quality, it is obvious. As I said, there will be delta P, delta Q mismatch. Because I have not done it intentionally. I have done it unintentionally. It has been done. So I don't know what is the delta P, delta Q status. So therefore, there is quite good chance that my voltage frequency will be deviated from its nominal value. And that is known as degradation in power quality. And grid protection interference, because one of my students, 2-3 of them are working like overcurrent relays, distance relays, differential relays, which are fuses, reclosers, which are dedicated for protecting this low and low voltage microgrids. They are going to be affected because the current level will be different, voltage level will be different, frequency based relay will be affected. So this, of course, the grid protection interface will be there. And very importantly, during islanding mode of operation, as the frequency and voltage varies, the controller of the inverters of the solar and wind system, they also switch its mode of operation. If they are operating like in PQ mode, they'll go to VP mode, voltage and active power mode of operation. So there is change in controller. And malfunctional protective devices, as I said, the overcurrent relays may be maloperated and equipment damaged and threats to personnel or crew personality. So what is this equipment damage? Like if you have some synchronous or you have induction motor based loads, so due to the frequency change, the loads which are sensitive to the frequency voltage variation, so those equipments may be affected. And one more concept, as I said, what is safety personal threat? Suppose these are my utility load sites, okay, and this microgrid is now disconnected, and let us say this grid, due to some disturbance, this switch is open, but however these utilities do not know that that grid is now off, but this microgrids like in the solar, wind, or SBDR means synchronous based DR like small hydropower plants. IBDR means inverter based DER. DR means distributed energy resources. So they will try to push some power to these loads. So these loads the worker who are working over here, so they know that the grid is off, but however, they're getting some power from other ends, renewable sources. So therefore, these people may get also shock. The safety matters. So therefore, this unintentional islanding detection must be there at the terminal of the renewable sources, like at this terminal. Here I'll just measure the voltage, current, frequency, impedance. And once I know it, so I have to de-energize these renewable sources quickly. So that de-energize, I said de-energize, not tripping. So de-energize means I have to do some manipulation at the gate poles. I'll stop the gate poles to the inverter converter of the solar panel so that the solar panel will stop energizing this grids, AC grids. Okay, so this is how we can save many issues which are happening due to the unintentional islanding mode of operation of the microgrid. So now I'll tell you a very interesting fact. Why this islanding? See, as I said in one of my talk that when you do some research, there should be some kind of motivation behind it. Otherwise, if you're walking, then you'll be just walking like this. You know, there is no motivation. Why I'm walking like this? Just I'm walking for publishing IEEE paper, taking my degree or something. I'm talking to the PhD scholars if anyone is present. I mean, in faculty forum also we should be. I mean, personally also I feel, but even though every time we cannot, but that should be our motto. That why we are doing this work. So there is the International Smart Grid Action Forum. Okay, and Smart Grid International. Under this, there is a branch, Smart Grid International Research Facility Network, and again under that, many countries actually are the member of this forum, International Smart Grid Action Network Forum, and there is a Smart Grid International Research Facility Network. There are also many annexures are there. So annexure 5. That is ISGN stands for your International Smart Grid Action Network, this one. Annex 5 is basically comes under us, India, Government of India. So again, Annexure 5, under Annexure 5, there are many objectives that Government of India has been assigned from this forum, International Smart Grid Action Network Forum. So the Government of India has assigned to many leading government industries like Power Grid, VHL, and like ABB. I mean, though ABB is not a government, but to some extent they are also participating. So they are actually participating to solve these issues which are coming under the Smart Grid International Research Facility. Under this Annexure 5, the power system testing comes one more branch, and under this branch, distribution grid protection reconfiguration is one of the major areas. And we are being motivated from there. Why not we will push some research to our country, and so that we can say a showcase thing that we are also moving, solving some problems in this area. So, and one more thing also, very recently this ABB, those companies are actually redirected basically that every inverter should, the inverters what you are manufacturing for this just interconnecting with the solar panel, it should be smart in nature, and it should, very importantly, it should have anti-aliasing feature also. Our grid supporting functions should be enabled over there. Okay, so these are actually the industry requirement and our mankind requirement. So therefore, research should be also should follow the same trend, so that we'll be more motivated. Even people may or may not ask us, doesn't matter, but at least we will be satisfied. Okay, so now coming to the techniques, there are many techniques, conventional techniques are available for detecting such unintentional islanding mode of operation of the microgrid. Because once I know it, I have to just stop the gate pulse of the converters, so that my solar or PV or fuel cell or batteries, they will be stopped powering to the network. And this operation should be within 2 seconds according to IEEE standard. That's the maximum time. It may be also with, like in Europe, it is within 0.3 to 0.4 seconds. In many other countries, within 1 second. Many other countries up to 2 seconds. So depending on their requirement and their reliability index of their network, so they have designed their standards. Okay. So there are so many unintentional island detection technique. The first one is a passive islanding detection technique. You can write it, but because I have not noted here. And the second one is active islanding detection technique. Third one is the hybrid. Hybrid means combination of both passive and active. And the fourth one is the communication-based islanding detection technique. Okay. So this passive, the passive name itself is kind of, we are not touching the controller or some inverter side of the solar or PV, solar PV or wind system or battery. We are just trying to measure the voltage, frequency, current or impedance at the terminal of the DGs. DG means distributed generators or DERs. And from there we will take some decision whether from those information we will take whether there is a grid disconnection or not. Grid disconnection means islanding operation. Okay. So there are many techniques like rate of change of frequency, phase jump detection, rate of change of power, rate of change of voltage. So these are some of the techniques I have written here. But why this rate of change of voltage? Because when there is a mismatch in active power, reactive power, so there will be change. Active power, there will be change in voltage. When there is change in reactive power, so there will be change in frequency. So therefore, in industry, they just taken up these two simple techniques quickly, and they are still they're in operation also. Rate of change of frequency, there is a frequency deviation from its zero value. Then what will happen? There is a islanding issue. But unfortunately, these techniques have two problems. The first one is, these techniques fail during zero power mismatch condition. What is that? Before 7 minutes, I was talking delta P, delta Q. What is that? Basically, your suppose your renewable generation and the load demand are not equal. But suddenly, sometimes it may happen that your same, whatever the load is present in the microgrid, same generation from the renewable present. So that means your generation is equal to your load demand. I mean, by coincidence, I'm talking, not necessarily every time it happens. So that is known as zero power mismatch condition. Zero power mismatch condition. That time, obviously, there is no delta P, delta Q. So obviously, there is no change in voltage, no change in frequency. So this technique fails. So we have to further go for active island detection technique. So active means what? Definitely, this is passive, I'm talking. So active means we are somehow touching some active elements. So can you just tell which are the active elements in this microgrid? Your converters, because converter inverters, they have the IGBTs, then they have this, they have the GTOs, they have diodes. So controller also there for the controlling the voltage frequency output of this operation of the inverter. So those are actually active elements. So active techniques, what the researchers again they thought of to overcome this issue. This is my NDZ problem, I said. NDZ means as you keep on increasing this square line, black one, blue one, red one, so keep on increasing it. So slowly, if it is shrink, means your mismatch in power is 0. And further, if you keep on increasing, mismatch in power increases. So this fails, this conventional technique fails for 0 power mismatch condition. Or it is in not 0, even it also fails for the power mismatch below 15%. It is also reported. But some techniques, they are also working fine for 0 power mismatch. We have also developed one, but that one I will not discuss here. I will discuss the active one. So this active islanding detection technique, the researchers, what they did, they tried to manipulate the controller of the inverter of the solar panel or your wind system or battery, mostly the controller of the inverters. They tried to manipulate. So what basically they did, some researchers, they tried to inject some disturbance in the controller of the inverter, and knowingly they are manipulating the voltage and frequency or voltage current at the terminal of the renewable source, and from there some indication they will get, and they will say whether the grid is off or on. Basically, grid is off means the islanding mode. Grid is on means the non-islanding. I mean, it's not a islanding mode, right? So they inject some disturbance at the controller of the inverter, and from there, when this inverter is affected by some controller of this inverter, then some manifestation, some change in frequency, voltage, and current will appear at the terminal of this DG renewable source. So then what will happen? Continuously 24/7 they have injected. What happens? What is the demerit of this technique? What they have developed is continuously they inject this disturbance signal. So obviously the power quality will be distorted every time. Even then the grid is not off, some disturbance in voltage and frequency, some disturbance. I am not talking 100%. So therefore, to overcome this, we have developed two techniques: active island detection technique in our laboratory, where we are not going to inject disturbance 24/7. We will inject only and only when the disturbance is there or some grid disconnection is there. So from there we will come to know. With some parameter, of course, we are measuring at the terminal of the DR, and from the parameter we will catch whether the grid is connected or disconnected. The first one is the frequency disturbance triggered D-axis current injection scheme for islanding detection. So these are some of the devices we are using. First one is the frequency disturbance recorder, FDR we call it. Takes digital samples 1 PPS signal as input, and it measures basically the frequency only. It doesn't measure the voltage and current. It is very fast, and its precision level is quite high. If I'm not wrong, it is around 0.0001 hertz. If there is that much of difference is there, it can catch it. It is so accurate in measurement. And so what we do in this process, let me tell. This is actually the inverter-based solar panel, and we are measuring these frequencies at the grid terminal as well as at the terminal of the solar panel. So these two frequency disturbances we will monitor time to time, and we have taken the difference of these two frequencies, FG minus FD, and if it is crossing suppose some threshold, then only we will inject this disturbance signal to the controller of the inverter of the solar panel. Is it okay? Now question comes, this extra thing FG minus FDG, this frequency disturbance is always 0 if the grid is not disconnected. It is obvious because the grid actually maintains the voltage and frequency at the PCC terminal of the renewable source. Remember this. But when this grid is off, so obviously now the frequency of these renewable sources may not be it is following to the grid. Because one more point, because there is no time, I could have discussed the controller part to some extent. This controller of the inverter takes the feedback signal from the voltage and frequency of the grid voltage and frequency. If the grid voltage and frequency is not available, so obviously reference to the inverter is lost. So therefore, during that time, if we'll inject some disturbance, then obviously it will just manipulate my voltage and frequency differently, and the corresponding impedance, if I take V by I, then it will be a good judgment parameter for me to basically decide whether the grid is off and on. So what we do, it is like this. This is the PQ controller of the inverter of the solar panel. So this is the D-axis side controller, this is the Q-axis side controller, and here we inject some disturbance signal ID star. And this DQ will be manipulated, and then it will be converted to ABC, and from there we will generate the pulse, and it will go to the VSC. The pulse width will be in such a way that our gate pulse width will be controlled, and the gate pulse signal will be controlled at the terminal of the IGBT. And accordingly, their operation will be stopped, or it will be, or in operation. We'll decide. So this is how this technique works. And here is a flow. I'll not go through detail of it. You can just download these papers from the website of my website in IIT Roorkee. It is present. Please go through it. It's a good paper, and if you have some doubts, you can ask me. I'll be very happy to clarify those points. Just I'm telling the steps in layman form what we are actually doing. The major portions I'm just telling to you. So after this disturbance is known, suddenly the disturbance signal will be injected to the controller of the inverter. And at the digital terminal, we are going to measure this impedance ZDH. So what you may ask me, this disturbance signal is actually 1% of the fundamental ID. Remember, and that is again not the fundamental. This is actual 30th hertz of the signal we have injected. So therefore, we are not disturbing the fundamental signal anymore. So this ZDH is nothing. This is the V divided by ID star, the disturbance signal magnitude and the corresponding voltage available due to that disturbance signal at the terminal of the DC. So this is our new parameter. Okay, so that will decide our decision whether the grid is connected or not connected. So these are some of the results. If there is some islanding, so this feature is quite large. This you can see the I'll not go in detail of all. Just you see this ZDH. So this is quite high when there is islanding, and the trip signal will be generated. And if there is no non-islanding cases, means there is some fault, capacitor switching, line switching, DG disconnection, so load disconnection or DG connection also. So those are basically known as your non-islanding cases. So there, this factor ZDH almost 0, so there will be no trip signal will be generated. And second one also we have created an active sleep frequency based islanding detection technique based on the another factor that here in the previous case we have injected the ID disturbance current, D axis disturbance current, but here we have injected the Q axis. We manipulated the Q axis of the current. There we manipulated the D axis part, and here we have manipulated the Q axis part. Why? You can see our paper. So on the detailed fundamental things we have written in the paper. So here one more device we have added is a micro PMU in place of the FDR. As in the previous technique, we have kept this FDR in this at the terminal of the grid and at the terminal of the renewable source. But here we are suggesting, can you just put micro PMU, because in this technique we need the voltage current information as well for calculation of our technique. So therefore the FDR will not help us. So FDR can only measure the frequency, it cannot measure the voltage and current. But micro PMU is such a device which can measure the voltage, current and frequency together with a timestamp. Because many of you maybe know that PMU, but micro PMU is the smaller version of PMU, and this is actually dedicated. This device is dedicated for only the distribution network, not the transmission level of the grid, a smart grid. It is only, you may ask me why this microgrid concept is coming, and you said microgrid, micro PMU. Why these concepts are coming in the smart grid? We never bother about the transmission level. And the first point is transmission losses should be reduced. And our distribution network is so much populated with loads, and renewable sources can be pushed near to the customers, and losses can be reduced, time can be reduced, infrastructure can be reduced, cost can be reduced. So from that point of view, the research is also moving. So now the micro PMU is booming. In booming stage, it is replacing the PMU. And PMU are placed on the transmission level. If my work is not focused on the PMU, my work is focused in smart grid in the distribution level. So again, further generation of this equipments are coming up. This micro PMU is one of it. So this micro PMU is one of the product from the California University, US. So in fact, in one of our project, we are ordering this equipment to have this bench, testing purpose in our microgrid bed. So Now this micro PMU can measure the voltage frequency, and it can it can be supplied to my PWM controller of the inverter, right? So inverter has one controller that may be NI controller or DSP based controller or APJ based controller, and inside that controller our codes will run. Okay, so then from there every action will be taken. So this is how the scheme. We manipulate the controller as in active islanding detection technique. Major role is in the controller of the inverter. Therefore, the name is active islanding. Okay. So this Q injection, Q reference, we are injecting to the Q side of the current, IQ. But in previous technique, we injected the disturbance IP current. So this is how it goes, and the corresponding ID and the pulse, gate pulse will be generated or not generated. It will be decided. So these are some of the flow chart, and this is some result. I'll not go in detail of the results. So like with our concern parameter, so the strip signal is going to be generated. And here we have rate of change of frequency. Here the frequency change. When the frequency change is going off certain threshold, then the islanding is detected and the trip signal is going to be generated. This paper is basically published in IEEE Smart Grid. It's a good paper. Maybe anyone of interested, you can go through it and you can ask me the doubts. Okay. So now, a very interesting fact is, what is this HIL test bed? Suppose we have some, basically in protection philosophy, let me tell you, unless until we implement in a HIL bed, we basically, mostly in smart grid, microgrid papers, I'm just looking, and in the industry also, people also looking. If you're not implementing in the HIL loop, then your technique is not validated. Why? Because suppose you are claiming in your paper or research that this technique takes 1 second for detecting my islanding, but not necessarily the same thing I felt take to a hardware bed or real-time implementation platform. So this may not work. If you're just simulating in a simulation like MATLAB platform or PSCAD, it may not satisfy my desire what the industry people wants. So what the industry people wants, industry wants, so that may not be fulfilled. So therefore, we have to test in a real-time platform. So in our IIT Roorkee, we have a real-time smart grid laboratory. This device, just my cursor is moving, is known as RTDS, real-time digital simulator. And here, all the modules are available in the library, like solar, wind, battery. I think now they have added the electric vehicle. This priority loads, non-priority loads, inductive, resistive, non-linear loads, linear loads, and then this total microgrid will run here, and we will take the data analog card. This is GTAO, giga transfer analog output card, and from there analog voltage current signals will take to the controller. This is DSP based controller, and then it will take the decision, and it will go to the GTAI, giga transfer analog card, and then it will return back to the RTDS. So in this process, this is a closed loop kind of process. This is known as HIL. H stands for hardware in the loop. L stands for loop. So this hardware is outside, controller is outside. I'm testing my technique is present here. So if my algorithm, whatever I discussed, it will run here, and I'll just take the signals to this outside controller, and it will fed to it, and it will just give a decision, and then your the gate pulse will be stopped, and your IGBT or inverter will stop powering to the AC grid. Okay, so sometimes we call it as CHIL also, but PHIL is something different. PHIL is different, but this is CHIL or HIL. That means what do you mean by real-time simulation? Somebody asked me also. I also thought it. So just it's a wall clock time. Suppose it is showing 1 second in my wall clock, means my watch. So the simulation also through this bed also I should get 1 second. That is what is known as a real-time simulation. And so all the techniques should be validated through this platform. And also we have one more laboratory called as Dr. M.P. Vasle Smart Grid Laboratory. But this laboratory recently we have developed, maybe before 2 years and 1.5 years, yes. And we are doing good. Like we have here solar, here the wind, a permanent magnets generator here, and we have this is a solar panel, this is a fuel cell, you can see some batteries, banks here, this is an inverter, So this is a filter banks. So everything is there. It is actually DC microgrid. It can also act as a AC microgrid. So it is in process. We are trying to improve this also, add more components, and we can do more research on the protection, maybe control or monitoring part of this. Okay, so with these 4 issues, I'll just conclude the protection issues of my this today's discussion. So I could stop myself if I couldn't. I'll tell these 4 issues along with the islanding. So as I said, islanding is the one of the major issues as far as the protection of the microgrid is concerned. And of course, in every now we are developing the inverters for this solar system. Mostly because why I'm talking solar because mostly the solar is easily accessible. At the rooftop of your building, you can just mount a solar panel, not a wind turbine. Near to your home or rookie town, we can just have a solar park easily, but we cannot construct a very big tower-based wind turbine. So therefore, I'm talking solar every time. So and this inverter-based solar panels are more peculiar in nature, fluctuating in nature, and they are more thief, you can say. This inverter-based solar panels create a lot of protection issues. And along with this solar panel, if we'll add some batteries and synchronous-based renewable sources, wind system, further the protection becomes more complex. And we should, researchers or industry, we should not afraid. We should rather accept the challenge and take some more massive simulation, do offline studies and do more online studies and some real-time simulation and get some conclusion from that. And what I'm trying to say, that the existing protection philosophy for the distribution network cannot work because those are static in nature. And now, due to this renewable integration like solar, wind, or battery, our network is completely changed. The power flow is bidirectional. So therefore, the voltage level decreases and increases, and current level decreases and increases. So there, obviously, we need a very dynamic protection philosophy. So the first issue is the dynamics in the fault current level and bidirectional fault current, fault stripping, blinding the protection. Let me just tell one by one. This I'll take 4 to 5 minutes. So what is this dynamics in fault current level? Let us say here is just some fault. Here is my microgrid and the main grid, and this is my DER, means my renewable sources are connected through this feeder, and these are my loads. So any fault occurs means that definitely the main grid will supply some current, and the renewable source will also try to supply some current. So this type of operation here, you see, if the grid is connected, so the fault current level will be something else, because there will be 2 fault current components. One is by the main grid and one by the renewable source. But here, if the main grid is open, means this circuit breaker is open, that is islanded mode, so there will be no fault current contribution from the main grid. The fault current only is going to contribute by the renewable source. That means the current level is reduced, isn't it? So that means there is a variation. Dynamics in level of fault current means there is change in fault current magnitude. Okay. And the bidirectional fault current means you have, let us say, you have a fault over here. The current is contributed by the DER, current contributed by the main grid. But if a fault is in this bus bar on the grid side, then the direction of the fault current is reversed. See, this grid was supplying power in this direction, but now this DER is supplying the power in opposite direction. This is known as bidirectional fault current movement. And what is fault stripping? Let us say you have on main grid, you have 2 feeders are out, then there is a fault in feeder 2. So this DER also will try to supply some current to this fault point. So, but there is no fault in feeder 1, but still this relay, if it is an overcurrent relay, this relay will also see some fault current and this may trip. And unnecessarily the feeder 1 will be disconnected. So this type of operation is known as fault stripping. And what is blinding protection? The blinding protection is nothing. When there is a fault in front of your main grid and distributed energy resources, so the grid will supply some fault current, that is a dotted line IZF, and the DER will also supply some fault current, that is IZF. So now what will happen, this relay will see less current because the fault current remains constant. So now this fault current has two components like IGF and small gf. But earlier, if the DE are not present, IGF value will be higher than this IG small f. But due to this DER presence, now this fault current contribution from the grid side is reduced. So that as a result, even though there is a fault, but the relay current is not sufficient for the relay to trip. This is known as blinding of, as if the relay is blind, it cannot see the fault. So there are so many amazing concepts are there. I'm just keeping in front of you due to time constraint few, and you can read by yourself. You can investigate more on this topic. And if any issues, good points, you can take your home, and some bad points you can reject. So that is how this is from my side today. Thank you so much for your patience hearing the candidates. I'm really thankful to all of you for joining this session and giving me scope to speak something regarding my research. So really I'm thankful to all my research scholars who helped me, and we have a good teamwork here in IIT Roorkee Electrical Department in Smart Grid Protection Monitoring Control area. And you people are most welcome to contact us. And mostly we are going to, very soon we are going to have a feedback and website in our department. So you can visit our updates. So research or publication. Thank you so much for your patience hearing. Yes.
Thank you, ma'am.
Yeah.
Yes, dear participants, if you have any questions.
Any questions, you people are most welcome to ask me. I'll be very happy to answer you people. Yes. How are you?
Fine.
Yeah,
Nice to
great. Yeah. Nice to see you.
Yes, thank you, madam. I want to ask you a question. Actually, you told about nanogrid and microgrid. What is the need for using nanogrid nowadays?
So nanogrid is actually the main building block of the microgrid. I have shown you one PPT there. The nanogrid is, suppose I have in Roorkee town, suppose in city. So we have, let us say, 4, 5, or 10, 12, or 20, 100 residential areas. We are just making some small nanogrids. And when those small nanogrids are connected together through a central controller, local controller, through a gateway, so those actually top of like 100 residential areas, they constitute actually one smart microgrid. That's all. The microgrid, it's in the smart grid, microgrid is the building block. In the microgrid, the nanogrid is the building block. So if you just further reduce, so nanogrid is the first building block of the smart grid. This is actually the layout forecast. I mean, how our vision is going, how it could be. But honestly speaking, it is not in the practical field. It is not implemented till date. So we are forecasting. We are just looking forward in this vision to do it.
What about that smart grid you told you are using it is for laboratory purpose, or you are giving some public
access also? Yeah. Now I think all of you should know it. But in IIT Roorkee, we know it. I am also one of the member. ISTEM. ISTEM means it is a national venture by the government of India. And IIT Bangalore is taking over this duty. And IIT Roorkee, every IIT, NIT, in fact, all the private colleges, government organizations, they are going to put in the website, in the ISTEM, the list of the equipments, list of the laboratories available, and this facility can be utilized by anybody through our country. And this ISTEM, you can log into the ISTEM, type on the Google ISTEM, and you can contact to the IIT Bangalore is the main center. They are the main coordinator. So and you can take the advantage from there. Of course, that will be payment basis, but that I don't know. But personally, I know that this much that anybody can access to the facilities of all over the country where the facilities are available.
Thank you, madam.
Thank you so much. So, any questions? Yeah, please go ahead.
Yeah, ma'am, for transient voltage stability, do we have any other better option other than ultra capacitor for energy, for dynamic load changes and all?
Yeah, so see, actually, honestly speaking, now we started this storage-based research, where actually in my protection schemes we use the lithium-ion-based battery. We have not used the ultra capacitors for storing purpose. Of course, the ultra capacitor is the best option than even lithium-ion. And further, let me tell you, the lithium ion is the best one because due to so many reasons, we have also tested. If you keep the ultra and the lithium ion, the smoothness in the transition of the voltage and current is much better than the ultra capacitor with the lithium ion. This much I can say from the production point of view. And it you may check with your stability issues.
But for transient voltage stability, we'll be needing something like ultra capacitor, no? Because battery will be giving a constant supply. So will it be able to, handle that?
Yes, it's a good point. So you're talking like if you just put some ultra capacitor, your transient stability problem will be solved, right?
Yes, ma'am.
Okay, so yeah, so the battery has many. It's a very good question. The battery has many applications. Even in protection, also the battery helps in many regards. Like somewhere some current level is very low, the quickly the battery will come to action and to supply the required amount of current, and the relay will not maloperate. Similarly, if you have some issues, some disturbances, some transient stability issues are coming, but certainly one suggestion I'll give you: what is the battery operation rate and your transient stability rate? These two times to synchronize. You can always try with this, but time of synchronization is very important. But in our protection too, fortunately, the smooth transition of this operation discharging mode of battery to the fault point is quite convincing as to the time is required for our fault detection, fault direction estimation, or disturbance detection process. So similarly, you have to be very careful what is the discharging rate and time is required for developing or you can say improving the standing stability of the system. The time should match. That is what I can suggest you.
Okay, ma'am. Thank you, ma'am.
Okay. Yeah. So any further questions, please? I'll be very happy and to share answer your question.
There is one question in the chat box that how far could the solar tree really solve the electricity problem of the society?
Yeah, this is a good question again. So, see, actually, honestly speaking, till date, you have seen, I hope, the initial, whenever I talk, like even in the class also, one subject is to be quoted in hierarchy, smart grid. I'm taking that class and course. So, mostly in India, our input capacity is 270 gigawatt. And what was the figure I have given? This renewables around 87 gigawatt. So you can understand what is the ratio now. Around 20 to 30%, 25% we have penetrated the renewables to our existing grid. And honestly speaking, we cannot integrate more than 50%. The government is declaring more than 40% because you may say that, okay, so whatever the amount we need, we can penetrate. That is impossible because our grid should withstand that facility also. That infrastructure should also, see, infrastructure means what? Depending on the equipment size, depending on the equipment design, depending on my cable size, everything should be redesigned, relooked properly. Like just I said, the protection issues, what was existing before the renewable integration, they maloperate. Because that kind of conventional protection scheme we cannot utilize for the microgrid system. Whatever the overcurrent philosophy you have used before 10 years, 5 years, that may not be possible with the distribution or microgrid system with solar or wind system or battery. And because it is very obvious reason, because their behavior is something different. So similarly, when the solar comes to picture, how much we can penetrate to the existing network, we have to see from our infrastructure of the existing network. It is just not like a game, whatever the amount of solar I can integrate or penetrate to the existing network. We have to sit and we have to see the planning and we have to offline studies required for that. So it is seen from the many discussions I can share with you. The government is planning at least 40% renewable penetration should be by 2030. Remember, we are not 100% full-fledged owner of the solar. And again, the major demerit of the solar is It is very intermittent and it is very uncertain in nature. And night time, of course, there is no solar energy utilization. So therefore, the storage system is very strong. It's only we are going to depend on solar. So that is the very next to dream level. But our technology should be that much of strong to access 100% reliability. And that is only possible after 20 years with a very good technology. But of course, at the same time, we should not say that no, we cannot penetrate because of why should do the research. Yes, we should do the research. Just like in Germany, the 90% power is from renewable. Think about it. But our infrastructure should withstand that we have enough solar and wind. Let me tell you, we have exactly the potential of wind. Around 300 gigawatts of wind can be generated from our wind. Very amazing. So that technology we have to develop, and we have many constraints: political constraints, financial constraints, manpower constraints, on-trend personality. So many things that we are lagging. So we have to overcome those things. Of course, we will be dependent 50% to 60% on the solar. Is it okay? Who asked this question? Am I correct? Is it okay? The person who asked this question? Hello? Dr. Abdul?
Yeah.
Yes, ma'am. Okay.
Yeah.
Yeah. Good afternoon, ma'am. Ma'am, I would like to ask one question. Can you explain the phase jump detection? What is phase jump?
Excellent. So shall I go to my PPT or just like I can tell you can understand?
Ma'am, just like that also, no issue.
Yeah. So phase jump means at the DC terminal or the renewable end terminal, what we do, we basically measure the voltage and current. Okay. Let us say you have an AC bus, and the AC bus, your solar energy, because the solar energy output is DC and it is going through an inverter and it is connected to the AC bus. So there the angle between the voltage and current is measured continuously, monitored continuously. So that angle is known as phase jump technology. That's all. Okay. So phase means phase angle. Jump means if it is grid connected mode, the angle will be something else. If the grid is disconnected, so when the it is a very basic electrical engineering concept. When the one part of the network is missed, and the impedance and the sources, so obviously our voltage and current phasors will be affected. So during your island, the grid is disconnected, the voltage and current angle will be something different. So therefore, this angle jump from one value to other value is known as phase jump detection.
Basically, it is the change of the phase angle.
Very good. Yes. Good.
Okay. Thank you, ma'am. Thank you.
Yeah. Thank you.
Madam, good afternoon, madam.
Good afternoon.
Good afternoon. Madam,
Yes,
I have a doubt, madam.
Please.
So generally, this microgrid concept, we are seeing that it is applicable for the remote areas like that we have studied. Why not we apply for this general place rather than remote area like distributed?
No, sir. It is not like that. I think you have missed one of my PPT. I kept this microgrid concept is valid for everything. You see, see, there are two types of zones of microgrid. Even our country is divided basically in national level. It is divided in three parts. The first one is your urban cities, semi-urban, and the remote areas. Okay. So in the urban cities also we have microgrid system. In the semi-urban also we have microgrid system design, and rural cities like off-grid operations where the grid is not possible. As I said, meaning grid and microgrid, that is also possible. Who said every whole region is divided into different areas depending on our requirement. So basically our demand decides which area we are following. So remote area is something else. As I said, mini grid sufficient because in remote areas we don't have any malls or we don't have any big industries or like some kind of. We have agricultural plants, we have residential loads. So there the mini grids concept or microgrid concept works. So it is for all. Yeah.
Thank you very much, madam. Thank you very much.
Thank you. So stop here, Afsar.
Yeah, ma'am. Thank you so much.
Yeah, thank you so much.
It was really wonderful. It was really very wonderful session, and you have explained in a very wonderful way, no doubt. So thank you so much, ma'am. Thank you so much for accepting our invitation.
Yeah. Thank you so much for all the participants. because I special give thanks to Dr. Abdul. He has invited me, so I accepted. But I am also learning from your side also many things. I am improving myself where actually
Well,
the focus should be placed and where the focus should be placed, so that we can do better research and better movement should be there in teaching and research also. And my request always every time, take the good part from me, and if anything wrong goes, so excuse me and forgive me. That is
that's
what is.
okay. It's your
Yeah.
goodness.
Yeah.
So, but a few participants are asking for PPT. So, if it will be available, then we will share shortly with the
Yeah.
participants.
Thank you so much. Thank you so much.
Thank you, ma'am. Thank you so much. Thank you, participants.
Thank you. Thank you. Can I stop now?
Yeah, sure, ma'am. You can left. No.
Good evening, sir.
Good evening. Good evening, Dr. Afzal.
How are you, sir?
Fine, fine. Actually, because of some fever, I was a little late.
Yeah, that's okay. Thank you so much. In spite of having fever, you are with us. So now, how are you feeling, sir? It's okay?
Yeah, I'm comfortable.
Confirm?
Yeah, definitely, definitely.
Okay, so shall I start, sir?
Yeah, please.
Okay. Uh, very good afternoon to all the participants. Today we have Dr. Ujjwal Kalla from MANIT Bhopal. Dr. Ujjwal Kalla received the MTech degree in Power Electronics, Electrical Machines and Drives, and the PhD degree from IIT Delhi in 2010 and 2015 respectively. His research interests include power electronics, power quality, flexible AC transmission system, renewable energy system, active filters, and electrical machines and drives. Dr. Kalla is a life member of ISTE and an associate member of the Institution of Engineers India. He was the recipient of the National Awards of Best MTech Thesis of ISTE in 2010, the POSCO Power System Award of Foundation of Innovation and Technology Transfer, Indian Institute of Technology, Delhi, and Power System Corporation in 2015, and the Grid Track 2015 Award of Power Grid by the Ministry of Power, Government of India. So, Dr. Ujjwal Kalla is associated with various research projects funded by various government organizations. So, today it is very pleasure for us that Dr. Kalla is with us. So, now I would like to request Dr. Ujjwal Kalla, please share your experiences with us, sir.
Thank you, Dr. Afzal.
Welcome, sir.
Am I audible to all of you?
Yes, sir.
And my presentation is visible?
Now it is visible, sir.
Okay. So, thank you, Dr. Afzal.
Sir, your voice is having some echo. I think that voice is not so much clear.
Now is it clear?
Yes, now it's better, sir.
Okay. So today we will discuss the design and implementation of analog voltage controller. Just. Yeah. Today we will discuss the design and implementation of analog controller for voltage and frequency control of small hydro power generation systems. So now is my voice clear, Dr. Afzal?
Yes, sir.
Now there is no echo.
थोड़ा better है, sir.
थोड़ा better है.
Yes, Dheeraj, is it okay? Is it okay for other participants?
Yes, sir. It is nice.
Oh, that's okay.
You can proceed.
Okay, sir. Please continue.
Okay. So again in this we will discuss the small hydro power generation using single phase self-acting induction generator and how to implement the analog controller for voltage and frequency. So I have worked in digital and analog both the control areas. So today I want to share my experiences with implementation of analog controller for voltage and frequency controller, small hydro power generation system. So see, this is the block diagram of the scheme. Okay. This is the block diagram of the scheme where the self-excited single phase 2-winding self-excited induction generator is used for small hydro power generation, and a small hydro turbine is mechanically coupled with the rotor of this self-excited induction generator. Again, as I had discussed earlier, it has 2 winding, main winding and auxiliary winding. Both are electrically isolated in this generator system. When we use the single phase induction motor as a motor, this machine as a motor, both the windings, main and auxiliary, are electrically connected with each other. But when we use the same single phase induction machine as an induction generator, both the windings are electrically isolated. Okay. So here both the windings are electrically isolated, and a big size capacitor is connected across the auxiliary winding, and a very small capacitor is connected at the main winding. Okay, and the rotor of this induction generator is squirrel cage rotor, which is mechanically coupled with the small hydro turbine. It is feeding to the consumer load, and this scheme is basically for the remote areas where they have very limited non-linear loads. Most of the loads are linear, only there this application is more suitable. Okay, for the very remote areas where the availability of the grid is very limited or not available. Okay, so here what we did, we are controlling the voltage and frequency of this small hydropower generator using a PLL based dump loading system. Okay, so we have connected a dump load system across the consumer load at the point of common coupling. Okay, so the main winding of induction generator and consumer load and this dump load, all three are connected at the point of common coupling. At the point of common coupling, all three are connected. Okay. Now here, what is the issue? Main issue is in single phase induction generator, the voltage and frequency regulation is very poor. Inherently, the voltage and frequency regulation of a single phase induction generator is very poor. So as we increase the load on the generator, the frequency and voltage of the system both decreases. Okay, so that we require to supply more and more reactive power to the system. Okay, so but here what is important, what solution we have find out, that we have connected a sufficient value of capacitor across the main winding in such a manner that at main winding the generator is generating a rated voltage in full load condition. Means the magnitude of capacitor, okay, the value of capacitor connected across the main winding will decide that how much voltage will be induced across the main winding. Okay, so the main winding terminal voltage will be decided by the capacitor connected across the auxiliary winding. Okay. Now there are two ways. Either I may switch different capacitor whenever the reactive power is required, or what we can do, we have connected a big size capacitor of such a value that when this generator is fully loaded, voltage is 230 volt. Okay. So if now because of a large capacitor is connected across the auxiliary winding, which is suitable for generating a rated voltage when there is a full load on this generator, rated load on this generator. But sometime if the consumer load will be decreased or reduced from the rated load, then the voltage and frequency will go high in the system. Okay. In order to avoid that, in order to control the system frequency under varying load, we have connected a dump load system. Okay, so this dump load system is diverting the surplus power into the dump load. Okay, because of this is small hydro power station, so water is falling down and small hydro power is freely available in the remote locations. Okay, in hilly areas. Okay, so you need not to have a battery, which is a very costly affair. By simply using this dump load, you can control the system voltage and frequency. So here we have taken the system frequency as a feedback variable for controlling the dump load. Okay, so we are modulating the amount of power which is being supplied to the dump load in such a manner that system frequency remain constant. Okay, earlier before this scheme I have reported to the international community, people who have developed the dump loading system with the voltage feedback. First time I have reported a frequency feedback system for a small hydropower generation system. Because of I have used frequency feedback because of it is more important in an induction machine system to maintain a constant frequency than a constant voltage. Because of whenever the frequency in an induction machine varies, the magnetization curve shifted to the different upward or downward direction. Okay. So in order to keep the magnetization curve in a same position, we have used a frequency feedback signal. So because of I had taken the frequency as a feedback variable, so system frequency will remain constant using the varying the dump load. Okay. So when the system frequency will remain constant, the magnetization curve will not be shifted in upward or downward direction. Only the point of operation on that curve will shift only. But now secondary, if the system frequency is maintained constant, means active power will be balanced in the system. So when active power will be balanced and everything has and the excitation has been given sufficient for the rated power, so the variation in the voltage will be only 1 or 2% only, maybe maximum 2-3%. Okay, and which is allowable variation in the voltage because of as per the norms plus minus 5% or 10% in some cases variation in voltage 5% to 10% is allowed. So here the variation in the voltage will be less than 5% because of the system frequency has been maintained at a constant level. Okay. So here what I did, I had used a small transformer with, as a sensing transformer. So I had built this system for low cost system and very low maintenance. So I have not used Hall effect voltage sensor here, which is very costly because of the cost of a Hall effect sensor is a 5,000 and induction motor is also a 5,000 to 10,000. So the cost of the Hall effect voltage sensor will be comparable to the other system. So that I have used only transformer for the sensing the voltage. Okay. So I have converted 230 volt AC into 3 volt AC using this sensing transformer, and this 3 volt AC has been converted into the square wave, and fed to the frequency multiplier section. So the output of this sensing transformer is fed to the zero crossing detector, which is made of a 741 IC. Okay. And a simple analog zero crossing detector. So this zero crossing detector has converted this AC voltage signal into the square wave signal, which was earlier it was sinusoidal. Input signal was sinusoidal, and ZCD has converted it into the a square wave signal. Now this square wave signal, now we have another block, frequency to voltage converter. So I had tried to convert this variation in frequency into the voltage, but the frequency variation in frequency was only 2, 3 or 4 hertz only in a single phase induction generator under varying load. So because of lot of noise was there, so my system was not capable of converting such a low variation into the voltage. Okay, because of noise was also there. So I have used frequency multiplication so that if there will be a 1 hertz variation in the input side, output side there will be a 10 hertz variation. Okay, but when I tried that, there was the phase difference between input and output. So then again the F2V converter information about the frequency was not coming correct. In order to make it correct, I developed an analog PLL based frequency multiplier system. Okay, so I have used an analog PLL based frequency multiplier system. So with the combination of single phase PLL and frequency divider, I had developed a frequency multiplier which converts this input frequency into 10 times output frequency. So if there will be a 1 hertz variation in the input side, there will be 10 hertz variation in the output side. So my frequency to voltage converter, which is the next stage, will easily detect this change in frequency. So this error will go to the PI controller, and the output of the PI controller is fed to the comparator and then to pendulum generator. Okay, so this pendulum generator will generate the pendulum pulses. Okay, in response to the error. So reference comparator has a reference frequency which is 50 hertz. Okay, so if this output frequency is other than the 50 hertz, then an error will be induced and this error will go to the pendulum generator. Okay, and pendulum generator will generate the pendulum pulses accordingly, and then it will go to the IGBT of the dump load circuit, and this IGBT of the dump load circuit, and it will vary the duty cycle of this IGBT which is connected in this dump load circuit. By varying the duty cycle of this IGBT which is connected in the dump load, it will modulate the power supplied to this dump load. Okay, so in such a manner that system frequency will remain constant. So the duty cycle of the IGBT connected in the dump load circuit is adjusted in such a manner that the system frequency remain constant and a surplus power is supplied to the dump load. So whenever the consumer load decreases, the remaining power is supplied to the dump load. Okay, in such a manner that system frequency remain constant. Okay, in dump load power circuit, a 2-pulse rectifier means single phase rectifier and a dump load is being connected. So now because of in this case only 2-pulse rectifier is feeding to a registry load, definitely this dump load circuit is a linear load. Okay, earlier the different researchers have reported in the literature in the international level, they have used 2-pulse diode rectifier with a high filter capacitor in its output. So they have used a high value capacitor in the output of this 2-pulse diode rectifier. Okay, so because of they have connected a filter capacitor. Sorry. Because of they have connected a big size filter capacitor in the output of single phase diode rectifier. This single phase diode rectifier based dump load system becomes highly non-linear. Okay, so the earlier reported scheme, this 2-pulse diode rectifier based dump load system was highly non-linear, whereas in this present scheme, what we have reported, this dump load circuit is perfectly a linear system and not demanding any harmonic current from the system. Okay, so there are 2-3 novelties and beauty of this scheme. The first beauty of the scheme was the system frequency has been taken as a feedback variable. Since the system frequency has been taken as a feedback variable, so the system frequency will remain constant and it will not allow the shifting of magnetization curve of the machine. So if you will take the voltage instead of this frequency, if you will take a voltage as a feedback signal, so magnetization curve will vary, and because of system frequency will not be constant in that case. So in that case, magnetization curve will be shifted, and if the curve will be shifted, so there is no meaning of controlling the point of operation on that curve, because of curve itself has been shifted. No? So the point of operation on that magnetization curve may not match with the magnetization curve, because the curve will keep shifting all the times. Okay, so we have used the frequency feedback variable, frequency as a feedback variable, so that because we have used the frequency as a feedback variable, so that we have not allowed the shifting of magnetization curve of this induction machine. Okay, so because of this curve has not been shifted, so only the point of operation will be moved little, and because of system frequency is constant, so active power will be balanced in the system. So the variation in voltage will be only 2-3 volt only. Okay, so that is a allowable variation in a renewable energy system, standalone systems. Okay, so another novelty of this scheme is we have removed the filter capacitor from this dump load circuit. Sorry, I had to take some hot water in between. So, another novelty is there in this 2-pulse diode rectifier based dump load system, because of we have removed the filter capacitor from this scheme, dump load scheme, so that hello. Because of we don't have large filter capacitor, so my dump load system is a perfectly linear system. So in any system, if you don't require the filtering of AC DC supply, you don't use the filter capacitor, because of use of filter capacitor will make your single phase rectifier system as a non-linear system. So it will demand harmonic current from the source. Okay. So this is all about my scheme, and this is the photograph of the controller that we have developed. You see one plus 5 volt, one plus minus 12 volt, and one 15 volt power supply we have developed, and then this is this semi-variable port and this 741 IC. These two has formed a ZCD 0% detector. Then this is frequency multiplier circuit. Okay, and then this is F2V converter section. Okay, then it go to inverter and buffer IC 4049 CMOS IC. Okay, and last is the PWM generator. So that is made of 3524 IC, SG 3524 IC. Okay. So see this sinusoidal waveform is the output of the induction generator. Okay, output of the induction generator was a sinusoidal signal, and it has been perfectly converted into a square wave signal using this ZCD. See, this low frequency square wave signal is the output of ZCD. Okay, then this output of ZCD is fed to the frequency multiplier section. Okay, so this high frequency square wave signal is the output of frequency multiplier section. So you can observe the effect of PLL here. That see the leading and trailing edge of ZCD signal. Leading and trailing edges of ZCD output signal are perfectly looped with the trailing edges of high frequency output of multiplier. Okay, frequency multiplier output. So because of frequency multiplier is made of analog PLL based circuitry, so because of that analog single phase analog PLL, so the trailing edge of my frequency multiplier output is looped with the leading and trailing edges of the ZCD output. So what is the meaning of that? Means frequency will be perfectly 10 times multiplied. Okay, frequency will be perfectly 10 times multiplied. Okay, so if these edges will not be looped, ZCD output and frequency multiplier output edges will not be looped. Okay, in that case, sometime this multiply will be 10.5 times, it may be 9.9 times, maybe 9.5 times, or maybe 11 times. Okay, but if both the signals are looped, both will remain perfectly looped, and frequency multiplier will give perfectly 10 times frequency output. And see here, whenever the frequency of the generator increases, the output of the ZCD also increases, and output of F2V converter, frequency to voltage converter, also increases linearly. It showed that F2V linearly responded the variation in the system frequency. Okay, so this test result recorded on the Agilent DSO, it shows that even during starting ZCD is giving output. So because of the output of ZCD, output frequency of the ZCD will be less than 50 hertz. So whenever it will be less than 50 hertz, the IGBT of dump load will have zero duty cycle, means it will not get any turn on pulses, so that no power will be diverted to the dump load during the starting of the generator. So once the generator will reaches to its rated value, then only the power will be supplied to the dump load. And see here, if even the generator voltage is distorted and even it become triangular, even then my frequency multiplier circuit is perfectly multiplying it and giving square wave output, and my F to V converter is giving perfect output linearly. Okay, so my system is perfect for distorted voltage signaling conditions also. See, when the voltage waveform is critically distorted, even then my system is functioning. This result shows that the uppermost waveform trace is the SEIG voltage. So if it is such a distorted signal, even then the system is functioning and dump load is maintaining voltage and frequency. So see here, so as the frequency in every cycle is increasing, okay, so duty cycle of F to V converter output is also increasing cycle by cycle. Okay, in every half cycle it is increasing. Okay, so my system is highly sensitive to the variation in the system frequency. Okay, and it is controlling the system frequency perfectly. Okay, so control output is being revised in every half cycle. Even during the half cycle, it is also being revised many times. Okay, so because of analog systems are very fast, so duty cycle increases from 0 to 1. So when frequency varies from 46 to 54. Okay, that is the nominal variation in the system voltage, and this is output of PI controller. And see, this is the power I have used 745 watt induction generator, single phase induction generator for implementation of this scheme. So see, generator output is 707 watt. Okay, and generator is operating at unity power factor, means dump load is not demanding any reactive power. Okay, and generator current THD is 4.3% and generator output voltage THD is 4.1%. So both the THDs are less than 5%. Okay, so my system is meeting IEEE 519 standards of the power quality, and it is generating output power perfectly. Okay, and see here, this is the performance of my system under varying load with controller, without controller. So left side figure result is without controller, and right side figure is with controller. Experimental results recorded on Fluke 43B power analyzer. Okay, so in the left side figure where the controller is not used, you can observe that system frequency is varying from 50.3 hertz to 52.3 hertz. So perfectly there are 2 hertz variation. Okay, from no load to full load. Whereas the figure presented in the right side, okay, that is also recorded on Fluke 43B power analyzer. You can observe in the lower trace that for the maximum variation from 0 to full rating, through variation in frequency only 50.1 hertz to 50.2 hertz. So there is a very only 0.1 hertz variation. Okay, so in this standalone system, variation up to 49.5 hertz to 50.5 hertz variation in frequency is allowed. Means one hertz frequency variation allowed, whereas in my system only there is variation of 0.1 hertz only. Okay, so this is excellent system frequency control. Okay, and see here, the left side figure is the dump load variation in dump load, and right side is the variation in the the left side figure shows the variation in consumer load. Okay, variation in consumer load, and right side figure shows the variation in dump load. Okay, so you can observe that whenever the consumer load decreases in steps, the dump load increases in the same steps, so that system frequency maintains constant. And whenever the consumer load increases, the dump load decreases in such a manner that system frequency remains constant. Okay, so this is the dynamic response of my system. And if the mechanical power delivered to the rotor of the induction generator is varies, usually in a small hydro system, input mechanical power remains constant. But during seasonal variations, it may be variation in the input mechanical power delivered to the rotor of the induction generator. So even in such cases, my controller is maintaining a constant frequency. So you may observe that variation in frequency is only 50.1 Hz to 50.2 Hz. Okay, so under sudden variation. So,
Excuse me, sir. PPT is not visible, sir. For the last half an hour, we are not seeing the PPT.
oh, we are not.
PPT is visible. Yeah, PPT is visible. Kindly pin to that particular presentation. So
Yes,
PPT
sir,
is
yes.
visible, no problem.
Okay.
You just pin to the presentation by Dr. Ujjwal Kalla.
Sir, not visible to me also, and it is not there.
It is visible for us.
You have to pin it actually.
Yes, you please pin particular presentation by Dr. Ujjwal Kalla. There is an option for pin. Yes, yes, sir. Please, you continue, sir. Please.
Madam, have you got it? Now is my presentation visible?
Yes, sir, it's visible.
Okay. So the variation in input power, sudden variation in the input power is not affecting to my system frequency because of I am taking system frequency as a feedback variable. Okay, so the system frequency is constant as well as the system voltage is also constant. So this is a very low cost analog solution for the remote areas. Okay, for a small hydropower generation system, and this is my patented scheme. Okay, I got one patent out of this scheme, and I also got one IEEE transaction paper. So this scheme is published in IEEE transactions on industrial applications. Okay, so IAS, IEEE transactions on industry applications. So modified electronic load controller, MELC. So this scheme is available online on IEEE Explore. Okay, so all contents, whatever I had delivered here, all these concepts are also mentioned in the paper, my paper. So by referring that paper, you can also learn all these concepts. So this is an excellent concept. I have worked on a number of analog controllers along with the digital controllers. So I have 3 patents on analog based controllers, and I got 3 transaction papers on analog control based systems. I have also published 11-12 transaction paper in digital based schemes, but analog schemes are also perfectly good and very low cost. So one limitation of the analog scheme is you have to develop a separate circuit for every application. Otherwise, that is excellent. In digital scheme, on the same setup, you can execute number of control algorithms. But as far as analog controls are concerned, for implementing any scheme which may be implemented using analog controls may also be implemented using digital controls. Any scheme which is being executed using digital control may also be executed using analog controls. So analog and digital and MATLAB, all these are the platforms. All these are the platforms. So important thing is your control scheme. Okay. So to develop the to create the novelty in the control scheme is more important than the platform you have used. Okay, then the platform you have used for implementing that scheme, because of it doesn't matter whether you are using analog control or digital control, or you are verifying your scheme with the MATLAB. Okay, but international communities nowadays are not relying on the simulation results because of a lot of fraud. Uh, Fraud ideas have been validated using the MATLAB's simulation. So nowadays, an international community is demanding the experimental validations of the control schemes. So it is very important for the research people nowadays to learn how to implement their control schemes. It is not a difficult task. It is very simple task. So just what you should start learning in this area. Okay. So now these are the conclusions. PLL-based controller has been designed and developed and implemented for constant frequency generator with voltage regulation of two-winding single-phase SEIG driven by a small hydro turbine. This single-phase SEIG PVC system has been tested in the laboratory to examine the suitability of the system at varying loads. The system frequency has been found almost constant under variable loading conditions. Overall cost of the system with the proposed controller is less in comparison to the conventional system, in comparison to the speed governor control systems, as the cost of the speed governor system is completely eliminated. Because again we are taking system frequency as a feedback variable, so that small hydro turbine will definitely rotate at a constant speed irrespective of the amount of electrical load on that. Okay, so second thing, because of a constant speed is maintained, because of constant speed of small hydro turbine is maintained, so the maintenance requirement in a small hydro turbine will be very less in this proposed scheme. Okay, and other modalities of the scheme I have already discussed here, and cost of this controller is much lower compared to speed governor systems, which is used in the conventional small hydro systems. So this is small hydro speed governor less small hydro system. Okay, so it did not require any speed governor on the small hydro. For your information, I would like to tell here that in all kind of standalone systems, usually we use speed governors in order to generate a constant frequency output from the generator. Even in DG sets, diesel engine driven alternator systems also, we use a speed governor in the engine which maintain the constant frequency of the generator output. Okay, in like that, in a small hydro system we also use speed governors in order to maintain a constant frequency output. So because of using this control scheme, already we have taken the frequency as a feedback variable, so the system frequency has been made constant using this modified dump load circuitry, electronic load controller. So the speed governor is not required to be installed at the small hydro turbine. Okay, So all these are the novelties of the system, but the limitation of the system is if you will connect the nonlinear load, so the system does not have the harmonic current mitigation capability. Okay. Otherwise, the system is excellent for consumer loads of linear type and in combination of small nonlinear loads. Some nonlinear load may be connected, but not full load should not be the nonlinear. So this is all about my scheme. Okay. So now we may open the system for query. We may open the session for query. You may ask any question to me regarding this scheme or any other power electronic converter, or if you are feeling any problem in implementing any analog
Participants. Yes, please, anyone, if you have any doubt, any query, or
Hello, sir. Good afternoon, sir.
Good afternoon. Good afternoon.
Sir, good afternoon. Sir, a small doubt, sir. Instead of small hydropower generation, if we replace in the PV generator,
Pardon?
PV generator instead of small hydropower generation, sir, instead of small hydropower generation, can I replace this hydro generator
Yeah,
with
your
a
voice
PV
is
generator?
breaking. Your
Then
voice
what
is
is
not.
the hello, sir?
Yeah.
Hello?
Yeah.
Sir, this is my doubt, sir. If instead of a small hydropower generation system, if we replace with a hello, sir.
Yeah. Please tell.
If we replace with a small PV generator there, and then what is the consequence, sir?
No, actually, then the everything will be changed now. So if you will use a small hydro is a different kind of source, and it is entirely different. You may replace the system by the using wind system. Okay.
Sir,
But you may not replace by the solar PV, because
sir,
if you have solar PV system, then you have to have some MPPT. Okay, because
sir,
of it will generate the DC power. Okay,
sir,
and
sir,
load is also AC. Okay, in that case, you have to have some inverter to
sir,
cater AC load requirements. So
sir,
because of inverter is not there in this scheme, so this
sir,
scheme may not be used for the solar PV systems. It sometime
sir,
it may be used for the wind systems, but it may not, never it may be used for the solar PV system because of inverter is not there in the system.
Okay. Thank you very much, sir. Thank you very much. Thank you very much, sir.
Next
So there is
query.
one question in the chat box. Which software is used to find the frequency variations of generator?
Here we have implemented the scheme using analog controller. We have not used any digital system, so no software was required here. Okay. Otherwise, if we are implementing the same on digital controller, then the estimation of system frequency will be required. Okay. So using MATLAB or C language, anything you may use for estimating the system frequency, that is not a difficult task. So using any software, you can estimate the frequency. It doesn't matter. So using MATLAB, you can easily estimate. Just you have to have a control algorithm and you have to write the code for your algorithm. So simply by detecting the zero crossing, you can also estimate the system frequency. But in zero crossing, if you detect there sometime voltage waveform may cross the zero ground line many times. Okay. So to avoid that situation, you may use the average filtering scheme. Okay, so that average moving filter. Today I am not well. Actually, I have very high fever, so that uh, my voice is not clear. So I am sorry for that. So moving average filter may be used. Okay, if you are using, if you are estimating the system frequency, okay, using DC control by using zero crossing method.
So thank you, sir. Thank you so much for your kind consideration. And dear participants, don't worry, Dr. Ujjwal Kalla will be with us in the tomorrow evening session also. So I hope that we will take more questions and more interactive session by tomorrow. So I hope I hope that Dr. Ujjwal Kalla will be having good health and he will be recovered very soon. I hope, sir.
Thank you. Thank
Please
you.
take care.
Thank you. Thank you, Dr. Thank
Okay,
you.
sir. Thank you. Thank you so much.
Thank you very much, sir. Thank you.
Thank you.
Yes, dear participants, kindly wait for the attendance link. It will be shared very shortly. Just 1 minute, please. Yes, dear participant, the feedback link has been shared. You are kindly requested to please fill the form.
Dr. Afzal, sir?
Yes, sir.
Sir, there are 2 times email address. So it is just to confirm the email address whether it is okay or some mistake is there, I think.
Yeah, I think kindly look, just update it. Sunil? Okay, let me check, sir. No problem. Yes, sir. Now I think it's okay. You please confirm. Rafi, sir?
Yeah, Afzal, it is okay now.
Yeah, sir, I think. Let me
Okay,
check.
okay. Okay, thank you, sir.
Thank you, sir.
Sir, actually, yesterday I am not submit the feedback form, sir.
Yeah, Ramesh. Okay, no problem. Dear participants, no problem, no issue if you will just forget 1 or 2 session feedback. So don't worry about it. Try to attend as maximum as possible, right? So if
Thank
you
you, sir.
will miss, you should not miss all the sessions at least. So if you will
Thank
miss
you, sir.
one or two, that is okay.
Okay, sir.
Right.
Actually, because of some internet issues, we sometimes automatically disconnected, sir.
Yeah, yeah, that's okay. That's okay. No problem.
Okay.
That is not hard. Right.
Thank you, sir. Nice organization. Nice.
Thank you. Thank you so much. Much.
So can we leave those who are filled the form?